Welcome back. First talk of this year, so I suppose I should say Happy New Year or something like that. It's getting on a bit. It's nearly spring. Anyway, it's great to see so many of you here. Really nice, and I hope you all had a good sort of Christmas, New Year, all that sort of thing. Oh, that's even better. Excellent. And hello, everyone online as well. I'll try not to forget that you're out there somewhere in cyberspace. Yeah, usual domestics, sorry to be boring. The toilets that still haven't moved. So if you need a toilet, go out of this door, turn right, and there's a door by the right-hand side of the staircase, and that will take you downstairs to the toilets where there are signposts. We're not expecting a fire alarm test, so if the fire alarm does go off, please leave in an orderly fashion out of the main front door from which by which you entered, and if you could gather in the piazza outside until someone tells you what to do next. So anyway, and just an experiment, if you like, that we're trying today. We're going to invite you to join us for coffee after the talk up in the council room. So that will give you an opportunity to ask more questions of today's speaker, and indeed to talk to each other, which we thought was probably a nice idea, and make the whole experience a little bit more social. So here we are, as I say, first talk of this year. Our speaker today, I'm very pleased to welcome Dr. Stephen Banham of Imperial College London. Stephen's a UK Space Agency Research Fellow and a collaborator on the NASA JPL Mars Science Laboratory mission, and also the ESA ExoMars mission. Steve graduated from Keele University with a master's degree in geoscience, and then moved to the University of Leeds to research fluvial systems in dry land environments, gaining his PhD in 2014. He worked for the British Geological Survey before moving to Imperial College in 2015 to collaborate on the Mars Science Laboratory project, becoming a research fellow in 2018. Stephen works on the Mars Science Laboratory project's MASTCAM instrument and has authored papers on the ancient surface environment and on the history of sediments in the Gale crater, also contributing to publications of the habitable environment within Gale. Habitable, we like that word. So today, Steve's going to tell us something about the Curiosity rover's visit to Gale crater and its ascent of the central peak known as Mount Sharp. So, Steve, over to you.
Thank you very much. So, yes, I'm Steve Banham, and today, rather than talking about actual habitability and astrobiology, I want to try and build an idea of how we know that the surface of Mars was habitable by reconstructing the ancient surface environment. So I won't be talking about sort of biosignatures and things like that. I'll be talking about the environment that these things could have lived in, and build up this idea that the surface of Mars could have been once habitable and the conditions were just right for life to have flourished. Like discovering ancient life on the surface of Mars is somebody else's sort of task to do. What I do is I'm sort of more at the base of the pyramid, sort of building up an idea of what the ancient surface was like, whether there was free water on the surface, and then looking at the ancient climate, sort of was there an atmosphere, what was atmospheric conditions like, did it rain, and then sort of from there you go into, was there like the right organic things, like was the chemistry right? This is sort of the astrobiology now. And then ultimately at the top of the pyramid, you have like astrobiology, whether it was there or not. So I'm sort of in this foundational area where you sort of need to understand the ancient environment before you can actually move towards the apex of the pyramid. But hopefully by the time I'm finished today, you'll be beyond a reasonable doubt that once upon a time, several billion years ago, Gale crater was indeed a habitable environment, and it was potentially the perfect place for ancient life to have thrived. So I'll start off with this image, which was taken about 100 sols after the rover landed. So the rover landed in August 2012, after a few tens of days of commissioning, where the engineers checked everything worked fine. we took this image of Mount Sharp, which is the central peak within Gale crater. It's about 5.5 kilometers tall, about 90 kilometers across at the base. And then it occupies the central part of Gale crater, and Gale crater itself is about 155 kilometers across, and it is about 5.5 kilometers deep. So Mount Sharp is as tall as the rim is on the side, which is important. So the understanding as of round about Sol 100 is that the sediments, and I'll talk a lot about sediments. So the sediments at the base of the crater, as viewed from orbit, they had a spectral signature which indicated that there was hydration of the rocks, and this indicated that there were these special types of rocks called phyllosilicates. Phyllosilicates are sort of the weathering product of rocks, where you have hydration of the rocks, and that can only occur where you've got water. So, at least for the bottom part of the crater, there was water involved during the depositional process. And then, as we go further up stratigraphy into the younger and younger rocks, things apparently got drier. There was more sulfates found in the stratigraphy observed from orbit, and this indicated that that Gale crater dried out during the period of time where sediment accumulated in it. So we go from sort of this wet, humid, potentially habitable environment all the way up into this dry environment. However, since then, on the lead up to this, we're actually on Sol 4452 of the mission. So this is relevant or up to date as of yesterday. Things are much more complicated than we expected. We've got of this wet environment in the base here, but then we have this veneer of sediment which accumulated in a very arid environment. We go up and over this ridge here, which I'll talk about shortly, where we're still within this wet environment. But then we get to this boundary here where it's supposedly dry, and we have this very complex history of drying and wetting and drying and wetting. But over time, this environment recorded by these rocks here got progressively drier and drier over time, but there was still opportunities within this accumulation here where there could have been a nice habitable environment. So this presentation is going to be sort of broke up into 4 parts. First, I'll talk about the initial infilling of Gale crater, where we accumulated these rocks, which we call the Bradbury and the Mount Sharp group. So this is the main sequence of sediments that accumulated. We believe that this pile of sediments actually filled up the crater to the rim, so there's about 5.5 kilometers of sediment. All the while the crater was filling in with sediment, things were happening in the subsurface, and we can get ideas of what was happening at maybe 1 or 2 or 3 kilometers depth within the crater, and what water was doing within the subsurface. We then have this period of exhumation where all of this sediment is no longer in Gale crater and it just disappeared somewhere. We don't really know where or how it got out of the crater, but it's no longer there. And ultimately, this resulted in the exhumation of Mount Sharp, which we can see here. And then there's a later stage of sedimentation where we actually have a veneer of sediment accumulated onto the flank of Mount Sharp, which is where we'll finish off. Okay, so again, just to give a bit of context, Mount Sharp in the centre, Gale crater, about 155 kilometres across. We're looking from the north towards the south, and this is Aeolus Palus, the location where Curiosity landed. So the rover sort of landed here where the laser pointer is, and then over the last 12 years, we've sort of driven along the side of this black band of sand. We crossed it, and now we're currently driving up into the foothills of Mount Sharp here. The rover that we have, Curiosity, it weighs about 900 kilograms, just short of a ton, and give you sort of an idea of its size. It's about the same size as a Mini Cooper. It's about 2.2 meters tall to the mast, so about yay high. This is the position of the camera systems here, mast cam and the nav cams as well. So most of the data I'll be talking about today comes from the mast cam. We also have a hand lens imager for taking close-up images of the rocks in this arm unit here. So this is the Marley instrument. And we can also get APXS geochemistry from this instrument here. It's essentially a portable X-ray fluorescence spectrometer. We have the ChemCam here where we can use a laser to shoot rocks. We basically vaporize the rock or the surface of the rock, and then from the sort of the ball of plasma that's emitted, we can do spectroscopy on that. If we want to do anything more detailed, we can actually drill samples with the drill on the arm. We can inject it into the belly of the rover, and then we've got a X-ray, a key-min instrument, which is X-ray diffraction spectrometry. This tells us what the mineralogy of the rock is. The other two instruments can't do that. And then we also have the AMS instrument as well, which does organic geochemistry. So this would tell us whether we had life in the sample or not. We have some other instruments as well. We can talk about what the capabilities of the rover later afterwards. Okay, so first we'll have a look at the initial infilling and get an idea that the surface of or the infilling of Gale crater was sort of dominated in its early stages, at least by like sedimentary processes involving water. So round about Sol 750, the rover had been driving. Oh, sorry. So Sol is a Martian day. So an Earth day is 24 hours, but Mars's orbit rotation is a little bit slower. So a Mars day is 24 hours and 37 minutes. So as a result of this, Earth and Mars times get out of sync. So this can result in planning on where we're trying to plan things happening on Mars in the middle of the night on Earth time. Complexities of sort of mission planning is that the days drift out of sync over time. And if you're working on Mars time, it means that you'll start going to work in the middle of the night to start the planning cycle for doing operations in the middle of the day on Mars. And over time, this drifts by about 40 minutes a day. So sometimes you get up at 8 o'clock in the morning to plan for what's happening on Mars at 8 o'clock in the morning. But then by the end of the week, you've already drifted maybe 4 hours. And when you're working on Mars time, it's difficult, but we don't do that anymore, fortunately. And I fortunately never worked in Mars time because I joined the mission about 1,000 sols after it started, when they started working on a regular planning cycle. Okay, so this is the Pahrump Hills, and this was quite an exquisite location. This is actually 250 days before I started on the mission, so I talk about this with nostalgia, even though I wasn't there. And this is where they sort of came to the firm idea that the rocks in the base of Gale crater were actually deposited in lakes. So we'll have a look at a few key outcrops in this area. So the interesting thing about the way the rover did science in this as an area is that the rover spent maybe about 200 days in this area, and it drove around about 3 times. So the first time it drove around looking for sort of the best outcrops to deploy its arm, to have a closer look at the stratigraphy, and also as well to do some basic geochemistry. So it drove around once taking pictures. It drove around a second time doing geochemistry using the laser and the arm. And then the third time around, they picked a spot and then they drilled. One of our colleagues on the mission likes to remind us that if this was a human geology doing it, he would have taken about 20 minutes to do all of this. But it took us 200 days to do this. And this is one of the limitations with a rover on the surface, is that you have to give it a set of commands. It'll go off and do that, and then it'll send back the results. And it's something that a human could have achieved in maybe 5-10 minutes. Take some pictures of these rocks over here, click, click, click. Done. What do you want me to do next? But that takes a rover a day nowadays, because the power is becoming progressively more limited. It can actually take 2 or 3 days to do the same thing. So the key so the rover deployed its hand lens imager, and it took a picture of these rocks. The engineers were like, okay, we've got some pictures of some rocks. The sedimentologists absolutely lost it. They were like, wow, look at this. We've got these rocks that are laminated. These laminations are about 0.5 millimeter thick, and they're uniform. You can trace these things for about 2 or 3 meters across the outcrop. And the geologists had already seen this on Earth. These are rocks that you would typically find in the bottom of a lake. So if you imagine a lake with a plume of sediment coming out of the top, the sediment will eventually start settling slowly through the water. It's dictated by Stokes' law. The smaller the particles, the slower they settle, but they settle out uniform across the lake bed. And these are what we're seeing here. So these are lake bed sediments. So this was sort of some of the first indication that Gale Crater could have actually been a lake once, full of water from one side to the other. The rover then continued to drive along, and we encountered some of these other more resistant rocks in the middle here. We sort of had a look at newspaper rock, and then we had a look at whale rock. And whale rock was another one of these sort of slam dunks where, when we looked at it, the engineers went, okay, weathering resistant, mechanically strong rock. The geologists went, wow, look at this. We've got these features called crossbeds, where we've got these cross laminations here, which sort of are inclined from one direction to the other. So these are layered rocks that sort of dip sort of like this. And the geologists were quite excited because if this video plays, this is essentially the process that happened. We have water flowing in a uniform direction, maybe about 2 or 3 meters a second. It picks up sediment in the flow, transports it up the back of the ripple, and then sort of as you get to this point here where the cursor's not moving to anymore, the sediment sort of falls onto the lee side of this subaqueous dune, and then it gets trapped there, and more sediment sort of builds up on the front, and over time the layers sort of build up like this, and the dune migrates downstream. If conditions are just right and more sediment's brought into the environment than is leaving, then these can actually build up in the stratigraphy, and you get these features called crossbed, much like you see here. So we're building up an idea that Gale Crater could potentially did have a lake in it. We had sediments being delivered from potentially from the crater rim and being brought out into an alluvial fan. And then over time, depending on what happened, the lake level may have dropped. This would mean that rivers bringing in these sediments and depositing these cross sets, these would move into the center of the lake. The lake level then might rise. These rivers would sort of jump back in the stratigraphy, and you would end up with these layers here, where this might represent a period of time where the lake level was low. Then this intervening section here, the lake levels then rose again. The rivers retreated to the fringes of the crater, and then again, so you've got the lake level sort of doing this sort of thing, and the rivers sort of doing this on the margins. And we can build this idea up just by looking at the stratigraphy. Everybody following me so far? Okay, good. Okay, so we found this at the sort of in the lower parts of the stratigraphy. So now what we'll do is we'll sort of continue moving up the sediment pile and see how things change. So one of the key features that we saw from orbit was this feature called the Vera Rubin Ridge. It was a weathering resistant layer, and it had a very strong hematite signature. It was called the Hematite Ridge at one point before it was renamed the Vera Rubin Ridge after the famous astronomer Vera Rubin. Very interestingly, Vera Rubin's son, Dave Rubin, was actually involved in the mission as a sedimentologist, and he's one of the foremost people who work on how aeolian bed forms migrate, and he had quite a big hand in some of the research we did on the Stimson Formation later. So this is quite a cool anecdote. So what did we see at the Vera Rubin Ridge? Well, the thing is we were driving to the Vera Rubin Ridge. We was expecting it to be extremely different, and it turned out to be relatively the same. These rocks were actually still deposited in lacustrine environments. We still had lake conditions sort of prevailing, but when we looked in closer detail, we still saw the horizontal laterally extensive laminations, which could be traced for sort of meters or tens of meters. But when we look quite closely, this was actually something Sanjeev at Imperial College noticed, is that we had these small cubic divots in parts of the outcrop. So there were sort of small angular corners where it looked like somebody had impressed a cube into the sediment. And Sanjeev said, "Aha! I've seen these before. These are crystal molds where you've had some cubic mineral which is soluble, such as halite. You've had a sort of a cubic crystal of salt form in solution. This has then fallen down to the bottom of the sediment, and then it's made an impression. And this indicates that the lake was potentially getting more saline at this point. And typically, if your salinity of your lake rises, this might mean that you have more evaporation or evaporative processes going on, which typically indicates that you're sort of accumulating like larger amounts of salt in the lake because you've sort of got evaporitic conditions and you're in a more arid environment. So we've sort of starting to get this idea that we're moving from perennial lakes to sort of ephemeral lakes, where sometimes the lakes are there for 1 or 2 or 3 years, but then in other periods of time, the lakes maybe completely dry out. And we might end up with an environment similar to this. So this is an example from the Atacama in Chile, where we've got these short-lived ephemeral brackish lakes. So not the best for habitability, but it's still habitable. We're still getting nutrients brought in. It's more saline than we would hope, but it's still a habitable environment. And this is sort of an idea of how things progress, where we sort of go into this model where we've got sort of a moat lake sort of forming around the central peak. And then over time, we've gone from sort of this one single continuous, maybe perennial lake to more isolated ephemeral lakes, which sort of coexist and sort of evaporate over and dry out over time. Okay, so now we're moving up towards the sulfate-bearing strata. So the last sort of model was for the upper part of these clay-bearing strata, and next we're going to move sort of up into the sulfate-bearing strata. This layer of sediment here, the Stimson Formation in the Green Hue pediment, we'll come back to this shortly. Okay, so just for some context, we've looked at the Vera Rubin Ridge here. We've just dropped down into this feature here called Glen Torridon, and the next place we're going to look at is Mount McCoo over here, which is sort of the transition between the lower phyllosilicate rocks and the upper sulfate-bearing rocks. So within this outcrop, there was sort of a kind of a stark transition. In the lower part of the outcrop, there was sort of these well-bedded, layered, laminated rocks, which we interpreted were formed in either a fluvial environment or a lacustrine environment. But then, sort of at this point here in the outcrop, there was a massive change in the stratigraphic sort of signature of what we saw in the rock, and it was overprinted with fractures and the sulfate. There was much more sulfates in these rocks here. We think there was actually some groundwater flow where sulfates were sort of brought into these rocks at a later date. So now what we'll do is we'll continue moving up the stratigraphy, and the next outcrop that we encountered was the Rafael Navarro mountain, and from sort of a few kilometers away, we could actually see that this outcrop was composed of these sort of large-scale dip-in cross sets. So these form in a similar process to those which I showed you at Whale Rock, but instead of being formed in a flow that was sort of a few meters deep of water, these were actually formed in a flow of air, which is a few tens of kilometers deep. And these are actually preserved ancient dune forms. So we've sort of gone from in the lower parts of the stratigraphy where it was all sort of dominated by fluvial and aqueous processes, we're now moving into an environment where it's sort of dominated by airflow moving sediments, and because the atmosphere is effectively quite a deep fluid, it means that you can sort of move sediments in a different way, and as a result of that, you end up with these large aeolian bed forms, and the rocks within this mountain are actually the preserved expression of large ancient dunes, which could have been sort of tens or hundreds of meters tall. However, within the stratigraphy, so this is the next hill along, Mirador Butte, we actually found some smaller lenses. So these rocks in the bottom here, these are characterized by these aeolian cross sets. So these were essentially large preserved dunes. But there were some smaller examples here. So the prow here, if we take a closer look, these were actually formed in aqueous environments. So when even within this large ancient dune field, which is represented by much of the rocks in here, we still have some inter dune corridors where we have water flowing, and these are the sort of the preserved expression of these, where we've got rocks containing symmetrical ripples, which is a close-up version. And these symmetrical ripples, these indicate that we still have shallow water. And sorry, lost my train of thought. Here's an example of some from Scotland. But essentially what we've got is, even in these interdune corridors, we've got sort of shallow, maybe 1 or 2 meters deep water where we're still accumulating sediment. We drove a little bit further up the mountainside, and we found this feature that we've been looking for a while, called the marker band. And when we arrived at the marker band, or when we were driving to the marker band, we weren't quite sure what it was, but we saw it from orbit, and we also saw it in long distance images. It's sort of maybe a 2 meter thick bed, which is weathering resistant. When we arrived there, what we actually saw on the top of it were these ripples preserved on the top. And again, we were amazed when we saw these, because we can tell something about the environment. So from examples on Earth, such as these ones here from the Triassic in Greenland, we have these symmetric ripples, which are sort of uniform on both sides. They sort of form a symmetric shape, but we can tell from these which direction the wind, or we can get a general idea of the azimuth of the wind. So these typically only form in 2 places. Either way, you've got tide or wave action, where where you're at the beach, where the tide's sort of coming in, and it causes that oscillating motion. Or alternatively, another place where it can happen is in a shallow lake, where the wind blows across the surface of the lake, and this causes the water body to oscillate back and forth. And if the water is shallow enough, this oscillating motion sort of transferred down to the sediment on the bottom, and it can actually cause the sediment to oscillate back and forth. We were able to measure the orientation of these ripple crests, and from that, we were able to determine that, based on the ripple crests being oriented sort of northwest, southeast, that the wind azimuth was sort of from either from the northeast or the southwest. So the wind was sort of blowing either in this direction or this direction. And hopefully I can show you a brief animation to sort of show how these ripples form. So you have the wind sort of blowing, it causes the water to oscillate, and then as a result, loose sediment is picked up with one current, pushed up onto one flank of the ripple, and then as the current reverses, sediment on the side is pushed up onto the other side flank of the ripple. You can see that over time, if you started a flat bed of sediment, over time this sort of grows up into like a chevron crested bed form. Hopefully this will work, but this just illustrates that when you start from a flat bed of sediment, this is how these ripples grow, and they sort of propagate over time and sort of get larger. If there's any defect, they sort of iron themselves out. It just demonstrates that if you have an unorganized pile of sediments, water oscillating in one direction or another, or transported in a uniform direction, these sand grains will organise themselves, which can then be found as a feature within the stratigraphic record. And depending on the periodicity of the oscillation, the ripples can grow in size or shrink in size, depending on your water depth and the period that the oscillations occur on. This is where I'll struggle. So the key thing to indicate from this is that many people talk about Mars being like a frozen place. So many people have ideas that that even though there was water on the surface of Mars, because it's further away from the sun, receives less solar radiation, most of the water on the surface of Mars should have been frozen. However, the key thing is that because we've got the wind blowing across the surface and we've got these ripples forming, this indicates that Gale crater was, at least at this point, not covered in ice. So we had a body of water that was open to the atmosphere, and the atmosphere was able to interact with the surface of the water and cause this sediment transport to occur. As we continue on up the stratigraphy, we're starting to see more examples of pinstripe lamination, and this indicates that rather than having large dunes, we've probably got sand sheets. So if you imagine a large barren flat environment just covered in sand with no dunes or anything like that, this is the sort of environment we're moving into now, where there's little topography and it appears to be dry. However, the key thing about sand sheets is that typically sand sheets require some amount of groundwater to actually cause them to accumulate. So if you didn't have the groundwater there, the sediment would not be cohesive in any way. And if you accumulate some sand, then all you need is more wind, and this would then essentially blow all the sand away, and then you would erode the sediments that you had accumulated. So what you actually need is groundwater sort of rising through the sediment that you've accumulated to stick it together and stop it from blowing away. So even though we are moving into this environment with sand sheets, we still have water in the environment, even though it's groundwater just beneath the surface, just making all the sediments a little bit sticky to keep them there. So again, you might think desert, not very habitable, but there's still water kicking around where it might not be habitable on the surface, but it still might be habitable in the subsurface. Okay, so that brings us to sort of currently where we are. So now what we'll do is we'll have a look at what happened in the subsurface. And while the rover was driving across all these lake bed sediments, one of the interesting things we saw is that these sediments were all fractured, and in many cases there were distinct types of fractures within the rock. And one of the most striking fractures we saw are these sulfate-filled fractures, where we have this white material infilling the fractures, where aqueous processes within the subsurface had sort of caused the rock to fracture. And then these fractures themselves acted as conduits for water to flow through. And then as the water flowed through the fractures, dissolved minerals within the water were then precipitated out into the fracture, filling the fractures with these white materials. Sorry, I'll skip this. And one of the things that we can sort of get an idea, we can actually sort of build an idea of what was happening within the subsurface. And this is some work that I've been doing recently on the mission to sort of understand what was happening in the subsurface. As an aside, this study sort of originally came from trying to determine if this cliff was actually stable. And when the rover drove past it, was there a risk of the cliff actually collapsing on the rover? So this cliff is about 12 meters tall, and the area that the rover drove through was about 10 meters wide. So there was actually a risk that as the rover drove through, the cliff could have collapsed on us and caused some damage to the rover. Fortunately, that didn't happen. But from that study, it then turned into a completely separate study, trying to figure out what was happening within the subsurface. So this is using some software called Pro3D, where using the stereo cameras of the mass cam, we were able to do a 3D reconstruction of the outcrop. And then from this 3D reconstruction of the outcrop, we're able to measure certain features and attributes of the outcrop, so we can sort of figure out how steep the outcrop is, and also as well if there are linear features intersecting the surface of the outcrop, we can measure their orientation and figure out what's going on. So while I've been talking, all of these different lines, which are largely vertical, have sort of flashed on, and these are some of the different sets of fractures that we've been measuring. And these fractures essentially form at different times during the burial process. So the yellow and blue fractures formed first during sort of the initial phase of burial. Then these green fractures formed shortly afterwards. These are limited in their length because the horizontal fractures acted as natural discontinuities. So the vertical fractures would sort of propagate up and terminate against the horizontal fractures. But then later there were these blue fractures, which sort of propagate all the way through the other ones. And these formed later after the other two sets of fractures cemented. And then these represent later deeper fracturing events. And essentially the yellow, the blue and the green fractures, these formed during initial burial, where essentially what happened was is that as the sediment accumulated in the bottom of the lake, water was trapped in the spaces between the sediment. As these sediment were buried to increase in depth, the pressure within these pores increased dramatically. And then eventually you get to a point where the force of the water pushing out onto the sediment is greater than the tensile strength of the rock. And this actually causes the rocks to fracture, and then the water escapes through these fractures. And that's what the first set of fractures, this is how the first set of fractures formed. And then these blue sets, these cyan fractures, these actually form much deeper in the basin and could have had a much deeper source of water, potentially hydrothermal water coming in from water sort of beneath the crater associated with like the initial formation of the crater. So this would be hydrothermal activity associated with that. But the key thing with this is that as the sediment's getting buried deeper and deeper and you're fracturing it and the water's being driven out, that water will go up and towards the surface. And that is important again for habitability, because even as the crater's drying out, you're driving water from sort of lower parts of the stratigraphy up towards the surface. And again, this could sort of preserve and retain habitability within the crater, extending that habitability window for longer. Okay, so we've sort of discussed the initial infilling of the crater and why it sort of represents the preserved expression of a lake, which then dried out. We've sort of had a look at what happened within the subsurface, and now we'll move on to what happened after sort of most of the sediment was exhumed out of Gale crater, leaving sort of the proto Mount Sharp, and what happened afterwards. And this is actually where I start my involvement in the mission. So this image here was taken at roundabout Sol 986, just as I was joining the mission. And it was actually the first task that I was put to working on. So the rover had been driving across these lacustrine deposits, represented by these sort of tan colour rocks. And then lying on top of it, there's this discontinuity here, an unconformity surface, which represents a break in deposition and indeed erosion. So what had happened is that, as I mentioned earlier, Gale crater had infilled with sediment, and then there was a period of erosion where it resulted in this unconformity surface, which is actually inclined. And then on top of this surface here, you then have younger sediments accumulate on the top of it. And essentially this surface here can be traced for several tens of kilometres across Mount Sharp. And you can trace the boundary between the lower, older rocks and the overlying younger rocks. And this surface sort of increases in elevation as you drive up onto the flank of Mount Sharp by about 400 meters as you go from where we first encountered it up towards the top, where the rover currently is now. And this was over about a 4-kilometer distance. So what were these rocks that we encountered on the top of this unconformity? Well, when we got to them, we saw that these rocks were formed of cross-bedded sandstones, similar to the ones that we saw at Whale Rock. So the question is were these crossbeds that were formed by fluvial processes, water, or were they formed by aeolian processes, so wind transport? So my first task was to determine whether these were deposited by wind or water. And through sort of a systematic study of measuring the thickness of the cross sets, which were about 1 meter thick, typically fluvial or aqueous cross sets are much thinner. These were quite thick. The measuring sand grain size distributions, they were all quite uniform, but there was a bimodal distribution of sand grains. And the sedimentary architecture, we were able to determine that this outcrop was deposited in a desert environment, and that these are the preserved expressions of migrating sand dunes. So something that would look like this. So this is a photograph from Swakop Mond in Namibia, where you have a simple dune. It's about 5 or 10 meters high, and these dunes are spaced about maybe 150 or 200 meters apart. But this is essentially the environment that these rocks represent. We were able to go a little bit further, and we were able to build a depositional model. So looking at the size of the cross sets, we were able to determine that these outcrops were formed by 10-meter high dunes with wavelengths of about 160 meters, and that the crest lines were actually sinuous. And another key observation as well is that, as I mentioned, the unconformity, so the surface of the unconformity dips towards the north, and these dunes were migrating obliquely across this surface. If it was a fluvial system, it would have gone straight down. However, these dunes were migrating obliquely across them. So another piece of evidence that these were wind-blown sand dunes. We then drove a bit further south, and we encountered some more outcrops with similar cross sets. But these were slightly different because there were, rather than having a single set of bounding surfaces, there were multiple sets of bounding surfaces. I shan't go into the detail, but essentially what this means is that rather than having simple dunes, we actually have dunes on dunes. So if you imagine a dune that is maybe about 200 meters high, it then has dunes which are 10 meters high migrating across the surface of it. This is quite cool because we can actually use this to reconstruct which direction the wind was going. So something I forgot to mention about this one is that these cross-set surfaces in here were dipping towards the northwest, which means that the wind was blowing from the southwest towards the northeast. So we can sort of constrain which way the wind was blowing, and we get an idea of how atmospheric circulation was going around about 3.5 billion years ago on the surface of Mars. However, from this part of the dune field, we can actually say a little bit more. We can say that we have seasonal wind variations. So these main dunes here, These were driven towards the north by sort of the prevailing wind. Well, superimposed on these were these smaller dunes, and these actually only form if you have a wind blowing at a obtuse angle towards the lee slope of the main dune. So we have like a dominant wind sort of driving sediment sort of towards the north, but then we also have a subordinate wind sort of blowing in this direction, which is moving sediment along the lee slopes of the dune. So we have a much more complicated wind regime in Gale Crater at this time. And then finally, as we drove a little bit further south still, we encountered another outcrop of the Stimpson at the Green Hue Pediment, and we found yet more evidence for a slightly different wind regime. So unfortunately, the slide's missing, but we had a close look at this outcrop here, and we were able to devise this model here. So we actually had an even finer scale model of the wind here. So essentially what happened is that you have a straight crested dune, which was migrating sort of towards the south in this case. So this is actually quite spectacular because, as with the other two examples, the wind was driving the dunes towards the north. But in this case, the wind is driving the dunes towards the south. So you've had a complete 180-degree reversal in the wind direction. And this must have persisted for maybe a few hundred or 1,000 years to drive a dune of this size in the opposite direction. So it was a persistent change in the wind direction. And then the other really interesting thing is that within the layers, we can actually see seasonal variations. So we have these features here called avalanche deposits, and these would form preferentially when the wind was blowing normal across the pan dune. And then we also have these wind ripples, which form typically when the wind is sort of blowing at a slightly different angle and blows obliquely across or along the face of the dune. So we've got these two interstratified units, which indicate at one period of time in the year the wind was blowing perpendicular to the dune crests, but then in other times we have wind blowing obliquely across, which results in these wind ripples. Hopefully this video will explain more what's going on. So this is a video I took the other year. These are the avalanche deposits, the tongue of black sand that's coming down. So we're looking straight at that was a little bit short. Try again. Okay, so this feature here is the avalanche deposit. And essentially what's happening is the wind is blowing straight over the top of the dune towards us. And this sort of causes the sand at the top of the dune to sort of collapse and move as this slow moving tongue of sediment down the lee slope of the dune. But then also as well, you can see sort of in here, you've got these ridges and these are ripples. So we've also got this subordinate wind blowing across obliquely across the lee slope from right to left. And this indicates that we've got more than one wind regime occurring within Gale Crater. So at one period of time in the year, the wind sort of blowing straight across the top. And then in other times of years, the wind's blowing oblique to this. So we have this sort of seasonal variation in sediment transport, which is quite cool. And this is something what the dune field might have looked like, where you've got these large scale sort of 100 or 200 meter high dunes with these smaller dunes superimposed on their flank. And from this, we were able to sort of reconstruct this ancient dune field. So initially, when we started off, we were sort of at the margin of the dunes where we had the simple dunes, where we first encountered the outcrops. And then over time, the rover sort of driven sort of through these outcrop, sort of going more into the centre of the dune field. Okay, and then finally, just for the last few minutes, so we'll have a look at this last evidence of water within Gale Crater. So the rover had sort of finished investigating these sort of turquoise-coloured rocks on the Green Hue Pediment, And then since then, it's sort of driven up and it's encountered these rocks in the Geddes Vallis Ridge. And these rocks here sort of derived from this channel area here. And there was sort of a notion that these were derived by sort of a landslide or a debris flow. And one of the most recent photos that we have is this taken here. So the rover's sort of driven over these rocks here, which are the layered rocks associated with the later drying out of Gale crater. But then there's this sort of chaotic jumble of rocks filling this channel in the middle here. And these are interpreted to be sort of the deposits of a debris flow. And what is a debris flow? Well, this video shows these are some of the most recent rocks in Gale crater, and this is essentially what happened. Oh, sorry, the video is not working, but essentially what you should see is sort of this jumble of sort of semi-damp rocks sort of moving down this canyon where there's lots of boulders suspended in a slurry of mud, and they're sort of coming down this narrow channel in a very dramatic fashion. Oh, no, that's not worked. It's all gone wrong. It's working. Excellent. Yeah, this is the same in maybe 3 billion years ago. This sort of damp, not particularly wet, debris flow coming down full of large angular boulders, the fine matrix of mud sort of holding everything in suspension. It's relatively dry. It's not where sediments are transported and never sort of to this most of the flow, and then some sediment sort of out along the top. So with this flow, it's mostly sediment that's the water in the flow. And even up there, it looks like it's quite damp. When it actually gets down towards us, it's actually like a suspended slurry of mud and rock. Okay. Oh no. Okay, so I think this brings us to the conclusion slide, where we can sort of get this idea that the history preserved in Gale crater by the rocks is actually quite complicated. So we sort of start off shortly after the crater formation in this wet environment, which would be very good as a habitable environment. However, it formed at about 3.8 billion years, so maybe it's a little bit too early for life. So the first evidence of life preserved on Earth is around about 3.5 billion years old with the apex chert. However, that's the first preserved evidence of life on Earth, and life on Earth probably extends back to maybe about 4 billion years ago. So this sort of formed in this Gale crater sort of formed in this golden habitability window, sort of at the same time on Earth. So it was a wet environment in the crater around about 3.8 billion years ago. So it's sort of in that habitability window, the same as Earth. But we're not quite at the time where we've got preserved evidence of life, but life could have still been in there. But then over time, as Gale dries out, we're getting closer to that period of time on Earth where we do actually have life preserved, but things are sort of starting to dry out and getting less habitable on Mars. And then we sort of go into this period or this sequence here where things sort of in a sort of a punctuated fashion, things sort of get wetter and then drier and then a little bit wetter and then dry, and it's progressively drying out. But maybe within this part of the sequence here, this is where we're sort of getting to like 3.5 billion years ago, where evidence was on Earth, evidence of life is on Earth, but we're still extending this habitability period, and maybe things are still habitable in this part here. And even after this, when we go into the deposition of this dune field, there was still water within the subsurface. So there's still potential for habitability sort of underground, either in the older rocks or in the younger rocks on the top. And then finally, as well, we still have enough water around in the environment to have this debris flow, where there is some water which could hopefully extend habitability up until quite recently, maybe 3 billion years ago. But who knows? We still have to look for it. And with that, I will conclude this presentation, and I will ask for questions.
It has been working. Thank you. Yeah. Something. Steve, thank you. That was extraordinary. I find it particularly interesting that Mars, I suppose for most of us, is still a kind of exotic and alien world. And yet, for you guys, it seems pretty familiar. You're finding stuff that you know all about is happening on Earth. It's really quite exciting and amazing photos. And I love the idea that you refer to we're driving around, like you're actually sitting on the back of this rover. So, are there some questions?
In terms of the wind blowing sound, have you any indication of what sort of air pressure?
That's a good question. So the air pressure now is about 4 millibars. So extremely low air pressure. Yet we still see sediment transported around by the wind. So Curiosity was actually parked by a patch of by the modern dune field, the Bagnall dune field. So the black sand that I pointed out briefly earlier. And it was a particularly windy period of time. And the descent imager on the bottom of the rover, they took a series of pictures over maybe a day. And the little ripples on the surface, they actually moved maybe 5 or 10 centimeters over the course of one day. So even though the Martian atmosphere is extremely thin now, it's still thick enough or dense enough to be able to move sediment on the modern surface. And these bed forms will migrate sort of centimeters over a period of days, and the dunes will migrate over maybe a meter or so a year in certain parts of Mars. But going back to these ancient dune fields, we're still trying to figure out whether the ancient, sort of how dense the ancient atmosphere was. So we're trying to figure out ways of trying to sort of back calculate how dense the atmosphere was based on things like the grain size. Would the atmosphere be capable of moving these slightly larger grains? Can we try and figure out migration rates from things within the stratigraphy? But the stratigraphy is like an incomplete record, and it's sort of an experiment that's happened. So there's a lot of sort of missing details that we're sort of having to extrapolate things from or try and fill the gaps to try and work things out. But yeah, we do think that the atmosphere was potentially thicker back then. It would make sense because water was much more stable on the surface back then. So you would need a higher atmospheric pressure to stop water boiling off at low temperatures that we experience on Mars today.
Do we have another question online?
No questions online.
So, recording the timescale of the last meteor impact at Arizona, which ended the age of dinosaur, is it possible for Mars to change its weather atmosphere?
Sorry, could you repeat that again?
Okay, so recording the timescale of the last meteor impact at Arizona, which ended the age of dinosaur, is it possible for Mars to change its weather atmosphere?
Yeah, so the meteorite impact that killed off the dinosaurs 65 million years ago, it would have affected atmospheric processes on Earth, but what happened with Mars is sort of a much larger scale thing that's happening or happened. So the current theory is that because Mars is a smaller body with a lower heat flow than Earth, what happened is because it sort of didn't retain the sort of internal temperature of its core. It sort of, if there was a magnetic field, well, in fact there was a magnetic field on Mars, but because the core was smaller, the core sort of froze and it lost the geodynamo that drove that magnetic field. And then because it lost the magnetic field, what happened is that the solar radiation could sort of ablate the atmosphere more easily. So the reason why Earth retains its atmosphere is because the magnetic field sort of protects us from the solar radiation. Mars lost that ability, and then essentially what happened is that the solar radiation basically just stripped the atmosphere away. As you lost the atmosphere, you lost the atmospheric pressure, which then reduced the boiling point of water. So the water would evaporate into the atmosphere, and then it itself was lost into the atmosphere. So it's a much bigger, slower, longer process than just a meteorite strike.
Okay, any more questions? This one, I think. This one,
This obviously is an history. I sort of mind that this gets a bigger extra of what Mars landscape is like. Can you use this to predict what it would look like in the future?
No, unfortunately not. We might be able to get ideas of what Mars might look like in future, and it'll probably be more of the same, actually. So Mars's surface has been quite stable for the last billion years. So the last billion years of Mars's history is called the Amazonian, and it's sort of been characterized by sort of slow sediment transport by the wind, by cryogenic processes near the atmosphere. So if you think of glaciers and things like that there are glaciers at the poles, but by and large, elsewhere on the surface of Mars, it's just sort of very slow, like gravitational associated processes where sort of the daily heating and cooling cycle sort of causes everything to just move very slightly. That might cause things to chip off very slowly, or the thermal expansion and contraction causes rocks to break up in a small way. Sort of large boulders might move up or down slightly, which causes smaller sand particles to get underneath, and eventually you get large blocks lifted off over millions of years. And I suspect that's what will happen for the next billion years on the surface of Mars, is that this slow wearing down of the surface will continue to happen, but I don't think there'll be any sort of fluvial activity, because most of all of the surface water is gone except for that which is locked in ice at the poles. Maybe that'll evaporate and into the atmosphere. There is actually like a very small water cycle on Mars. So there is an idea that sort of ice can form on the surface and then sublime back into the atmosphere. There are clouds on Mars as well. So you get these sort of icy clouds sort of high in the atmosphere. So Curiosity rovers imaged some of these. There was just a press release the other day as well where they showed these clouds sort of moving over Gale crater, and the rover was able to visualize it. But in general, it'll be sort of a slow decay. Maybe if you go to the Tharsis region, there's still active volcanoes there. They haven't erupted that we've seen in the last 100 years, but they are still interpreted to be active. Maybe one of those might erupt and something exciting might happen there, but we don't know.
Thank you for a fascinating talk, expressing the possibility of the environment supporting life. Has there been any evidence from any of the possible markers of biological life that looks like we vary between these the areas of the wet zones, trace vents?
Yeah, so I can't remember the name, the drill site. I think it was the Cumberland drill site, and I can't tell you when that was in the mission. But sort of down in the phyllosilicate units, when the rover did drill a sample and then put it into the SAM instrument, they were able to find sort of the chemical precursors for life within that sample. So if you think of things that you could eventually reconstitute into amino acids and proteins, which then could go on to form life. It's the things that you would use as the building blocks to make the amino acids before you then went on to making more advanced life. So they found the ingredients. It's like going into a kitchen and finding all the ingredients for a cake, but no evidence of the cake. Like cake or the life could have been there, but we've just seen the ingredients, but we don't know if the ingredients were combined in the right way to make life. Another complication is that so the Martian surface has got a lot of chlorite ions in the surface, so it's like oxygenated chlorine. It's essentially like bleach. And the way they do the chemical analysis is they take in a ground sample of rock, organic molecules and everything and these perchlorates, and they put it in a oven and then they heat it up to about 800 degrees. And the problem is that when you heat up bleach and organic compounds to about 800 degrees, they all react violently. And if you did have any large organic molecules, which could have been a biosignature, these basically get broken up into small components. So you only ever see small short chain organic molecules, because if there was any long chain molecules in there, they would have reacted violently with the bleach at 800 degrees. So, well, the perchlorates at 800 degrees, and they thought thermally decompose, I guess. So if this is one of the inherent problems with the SAM instrument, is how it works, and also the perchlorates on the surface. This is a reason why we could ideally do with sample analysis return. So the Perseverance rover's been collecting and caching samples. If we could get those back to Earth, then we could do different geochemical methods to determine if there was any biosignatures in there. But we'll have to wait for those samples to be returned to Earth.
One last question. Is there one? Are you saying that basically Mars is inorganic, or is there a percentage of organic matter in it?
There's a percentage of organic matter, a very small one. It's kind of like saying is the surface of Earth organic, and it's probably like in the whole bulk of the planet, it's like maybe 1% or something like that, and then everything else is like inorganic minerals and things. But yes, there are organic molecules, and when I say organic, it'll be like in the chemistry sense, organic molecules, like carbon, oxygen, and nitrogen, yeah. But it's a very small percentage. I'm not sure what the percentage is. It'll be a fraction of a percent, but a detectable fraction of a percent.
Okay, I think